Thanks, Jim. Let's switch gear a little bit in a more focused group where the gene tree is a lot more informative. All right. So, yeah, Caryophyllales is quite a diverse and quite an old group with 11,000 species in 34 families. It's a neat group. It has multiple evolution of salt, heat, and drought and cold adapted lineages, as well as multiple evolution in C4 and CAN photosynthesis. It also is the only plant lineage have the betylene pigment as seen in sugar beet and has quite a diverse carnivorous plant group. It has 3 genomes available, which is nice for analyzing transcriptome data. So we are interested in not only the species tree, but we're also interested in gene family evolution. Specifically, we're interested in what are the phylogenetic and functional locations of gene tree discordance, gene duplication, and shift in substitution rates. And we're also taking a more targeted approach to look at the molecular evolution of genes involved in pigment and carnivory. So this is not trivial because typical phylogenomic data set has a lot of missing data. And this is a data set with x-axis is orthologs ordered by high taxon occupancy to low. So as you can see that only very few genes have all the taxa. However, our benchmark analysis using 1kp data shows that with the typical 1kp data set, we can assemble 50% of total genes in the genome with low level of chimeric sequences. So our phylogenomic data set should be something like this with housekeeping gene and some of the gene that only express in certain tissue type in certain times. So we will argue that orthology inference, we can take a phylogeny-based approach to separate ortholog from paralogs. A lot of orthology inference pipelines start with the all-by-all blast and Markov clustering that iteratively get gene family from based on the blast hits. However, this approach is not biologically informed and often break up gene family into non-monotypic. We realign make tree again to optimize alignment trees. And then we extract rooted in-group clades that are separated by outgroups. Therefore, we get these rooted homologs that are by themselves can be used for various analyses of gene family evolution. We can also go ahead and prune ortholog from paralogs. So we did this in Caryophyllales with 69 in-group transcriptomes. We were able to get more than 10,000 homolog and ortholog with sufficient amount of data. And we made a species tree with more than 1,000 orthologs with 92% gene occupancy. And we make this species tree not just for a species tree, but we're interested in gene tree discordance. I would say that all the slides after this were using homologs. Basically, what we did differently here is that we mapped bipartition from homologs with gene duplication and everything on it to the species tree. And we can see that blue means homologs, percentage homologs will support the species tree topology, and green is the homologs support the main alternative topology, and red is homologs support the rest alternative homologies, topologies. And gray means homologs uninformed, basically bootstrap less than 50%. So you can see that there are quite a bit of gray uninformed homologs along the backbone, but we have quite a bit of blue in deeper nodes, shallower nodes, but we also have spots with quite a bit of green. We did coalescence simulation, found that coalescence by itself cannot explain this kind of pattern. So some of the area we're taking we're looking deeper into some of the reticulate area. So we went ahead to look at substitution rate heterogeneity And we realized that most heterogeneity happens as correlated with life history changes. So we mapped 5 woody herbaceous sister pairs. And we mapped, calculated 3,000 homologs for each of the woody herbaceous pair. And we found that both synonymous and non-synonymous rates in herbaceous lineages are up to 3 times their woody relatives. And this regardless of switches from woody to herbaceous or herbaceous to woody. So, which means this is driven by mutation instead of selection. And we also mapped gene duplication onto the species tree. We found 6 hotspots of gene duplication. 3 of them are known genome duplication from the outgroup in eudicots, and 3 of them are within the Caryophyllales. And we further went ahead to the synonymous distance plots. And by combining synonymous distance and mapping hotspots of gene duplication, we found a total of 14 Pleiadian polyploidy events in Caryophyllales. And this is about a year-old data. And currently, after doubling our taxon sampling in Caryophyllales, we actually currently have found 26 Pleiadian polyploidy events. This is quite remarkable. These are all only Pleiadian polyploidy events, not counting the ones on the tip. So Pleiadian polyploidy probably happen a lot more often than we previously thought. We also look at functional hotspots of gene duplication and retention. We found 2 functional categories that pops out, including signal transduction, including disease resistance and pollen recognition genes. We also found a lot of genes that deal with oxidation stress. Specifically, there is phytoquarm P450 gene that encode a key enzyme in the betaline synthesis pathway. So the betaline synthesis pathway is one of the short pathway in plants. It basically starts with tyrosine and produce either red or yellow pigments. And there are 2 key enzymes in this pathway, which is phytoquarm P450 and DOTA. We found that these 2 genes are actually only 50 kb apart in the beta vagaris B genome. And both of them went through segmental duplication followed by neofunctionalization in both enzymes. And the location of duplication and neofunctionalization happened right at the onset, switching between betaline, from anthocyanin to betaline. And betaline was lost for at least 3 times in Caryophyllales, then switched back to anthocyanin. We found that at least in the case of Caryophyllales, the switch is through deletion of both of the key enzyme and upregulation of anthocyanin pathway to reverse to anthocyanin. So this is gene deletion versus regulatory changes to produce this reversal. This is a work in progress. Currently, we are increase our taxon sampling through fieldwork and botanical garden collection. We're targeting over 3,000 transcriptome in the Caryophyllales. We also use a slightly different methods of building a core homolog set for sorting the rest of the homologs. We're looking at polyploidy versus speciation and niche evolution. We're also trying to correlate the expression and molecular changes to the repeated evolution to salt, cold, and defect adaptation. We're also playing with a little bit differential gene expression in carnivorous organs. We're also testing the metabolic operon hypothesis of the betaline synthesis pathway. With that, I'm going to acknowledge 1KP collaborators, as well as the people who help us in the field and lab, and people in the Smith lab in the University of Michigan. Funding is provided by University of Michigan as well as NSF. With that, I'll take questions.